Good afternoon, students. Let us start the class. Yesterday, we were working out this particular exercise where it is asked to construct a binary code using Shannon-Fano procedure, and it is also asked to construct a ternary code using the same procedure. So, today, let me tell you what is the meaning of a ternary code. In general, binary code will have only two symbols, let us say 0 and 1. Whereas in ternary code, we can add one more symbol, let us say 0, 1 and 2. Similarly, in a quaternary code, we can add one more symbol called 0, 1, 2, 3. This way we can go on. Now, you may think that information is always transmitted in binary as 0 and 1, but fundamentally it is like that. But we can have different waveforms. For example, when you think about 0 and 1, you will think about 0 volts and let us say 1.8 volts. I'm giving a typical example of this VLSI lab where we are using the 180 nanometer technology, and there the VDD is 1.8 volts. So you may simply think that 0 is 0 volts and 1 is represented by 1.8 volts. That is for a normal standard binary communication. We can have a ternary waveform there, which means we can have a waveform which is 0 volts, then 0.9 volts, then 1.8 volts. We can have it this way, where 0.9 volts will be VDD, and 1.8 volts will be 2 VDD, and 0 volts will be 0 volts. So, we can have waveforms which can represent more number of information with the lesser number of cycles. That way, we will have different types of waveforms. In the next semester, you are going to study a course called Digital Communication. There you are going to study about the baseband modulation methodologies. They are going to study about the different methodologies in which one waveform will contain more than one bit. In general, we think that one waveform will contain only one bit, either 0 or 1. But we can make the waveform complicated in such a way that it can contain more than one bit. For example, if the waveform is containing these three amplitude levels, 0 volt and 0.9 volts, let us say 0.9 volts is VDD, then we can have 1.8 volts. Similarly, we can have 0 volts, 0.9 volts, 1.8 volts, and then 2.7 volts. If at all we have a waveform which is containing these four states, four voltages, then it can be a quaternary waveform, where using the different waveforms combinations, we can represent more amount of information with the single waveform. Again, when you come to 6th semester, in that course called Digital Communication, you are going to study about the digital modulation methodologies, where you are going to study about ASK, FSK and PSK. So, in PSK, it is possible that one single waveform will represent more than one bit, because this QPSK will have 0 degree and 45 degree and then 90 degree, then 135 degree, then again 180 degree is nothing but 0 degree. That way, we can have these many phase shifts. For example, in QPSK, it can be 0, 90, 180, 270, 360. It can be that way. So, one cycle of 360 degree can have 4 phase shifts. Then we call it as QPSK. The same waveform can have 8 phase shifts. The example which I told you in the beginning, that is for 8 PSK. That is 0 degree, 45 degree, 90 degree, again 135 degree, 180 degree. That way it can go on. There can be 8 phase shifts. Now, with the combination of such different phase shifted waveforms, it is possible to represent one waveform for different numbers of bits. For example, if the QPSK waveform is used, we can have 0001, 1011. If 8 PSK waveform is used, single waveform will represent 3 bits. That means from 000, 001, 010 like that till 111. Because there are 8 phase shifts, a single waveform can represent, a phase shifted waveform can represent 3 bits. That is when I have been telling you that we are conveying more and we are going to transmit less. Now, if at all we construct a ternary code for the same information source which is given, then we can represent the symbols using 3 codes. Instead of 0 and 1, we can have 0, 1 and 2. And then we can have different waveforms for representing these 3 codes. How to represent the codes using waveform is going to be studied in the next semester only in the digital communication course. Now let me continue to discuss the ternary code. Now the second step is ternary code, where we have to divide this alphabet set into 3 groups now, so that each group will have approximately same probability, which means 1 by 3 is 0.33. So A is already 0.33. Next one, B, is nearer to 0.33, is 0.25. So it can be grouped this way. And all the other things are grouped in a single group now. So 0.33, 0.25 and all these things. Now even if you do, let us say, some other change here, it is possible that you will get another code set also. It is not mandatory that you will have to take 0.25 separately and 0.15 and 0.12 separately. If at all you club this 0.25 and 0.15, it is only 0.4. So it can be kept that way also. B and C can be kept as one group. D, E, F, G also can be kept as a separate third group. It is possible, but you will get a different type of code. But both are good codes only. Anyway, now we are arranging the symbols in the decreasing order, and we give the codes now as 2, 1. Then for the third group we give all 0. Now again, afterwards we divide this again into 3 sets or 3 groups, 0.15, 0.12 and these 3 together. Then we have this again 2, 1, 0, 0, 0. Lastly, only 3 are there here. Those 3 can be represented again with 2, 1, 0. So you have a code which is 2, then 1, then 0, 2, 0, 1, 0, 0, 2, 0, 0, 1, 0, 0, 0. These are the codes. We will find out the average number of bits per symbol. Now it is not bits, it is called trinits. Earlier it was called binary units. Now it is called ternary units, or we can call it as trinits. So we are getting it as 1.57 trinits per symbol. The procedure for calculating this L3 is the same as the earlier one. Now the efficiency here is we are getting around 97.83% when compared to the earlier one where it was 97.77%. That means there is an increase in the efficiency. There is a slight increase there. Here, why we are dividing by LG of 3? Because H of S we had calculated using the binary information. Now we are using the ternary information. So that H of S we have to divide it by LG of 3. That becomes H3 of S now. And divided by the L3, that we get around 97.83%. So the redundancy is 2.17%. Now the code trees are written for both of them in this fashion. The binary code can be represented in this fashion from the source again A, B, C, D, E, F, G. I had told you yesterday how to write the code tree. We can start with the 1 at the right side, 0 at the left side, and then we can go on. We can go on for each code, we can keep on representing finally for all the symbols. Now the ternary code is represented this way. For A it is 2, for B it is 1, then 0 is this side, again 2, 1, 0, again this side 2, 1, 0. So A, B, C, D, E, F, G are represented in the ternary code. Now you can see that the code tree for ternary code is smaller than the code tree for binary code. And the ternary code is easily arranged when compared to the binary code. Yesterday I had told you that we are going to write maybe a MATLAB program or maybe an algorithm for the ternary code or any type of code, and that can be saved in the system's memory, and it can be utilized for transmission as well as for reception, not actually for encoding as well as for decoding. So this is the ternary code. Now the Shannon-Fano algorithm is also called as prefix property. What is meant by prefix property I am going to discuss a little bit later, because of the instantaneous nature while decoding. What is this instantaneous nature I am going to discuss a little bit later, okay, because we are going to discuss now the properties of codes. There are 5 different types of codes, out of which one particular property is called as instantaneous property. This means that if the code can be instantaneously decoded at the receiver without waiting for the succeeding bits, then such a code is called instantaneous code. Anyway, let me tell all the details now when I discuss the properties of the codes. So let us see the properties of the codes. Coding can be defined as the transformation of source symbols into some respective sequences from the code alphabet. For example, if the source symbols are S1, S2 up to SQ, and now we have this character set X in which we have only 0 and 1, because any type of symbols we are going to represent using our alphabet set or character set. Now this 0 and 1 is called as code alphabet, whereas up to S1, S2 up to SQ is now the number of symbols present in the information source. For example, again if I take the English language, S1, S2 up to S26, there are 26 alphabets. That is nothing but A, B, C, D up to Z. All these 26 alphabets will be represented only by means of 0 and 1 in the ASCII code if it is a fixed length code. And again it is represented only using 0 and 1 even in the variable length code like Shannon code. Now in that case, we have a character set or alphabet set that is containing only 0 and 1. Now, the symbols S1, S2 up to SQ have to be represented in terms of the binary code alphabet 0 and 1. So, for facilitating the efficient decoding at the receiver, the codes are supposed to have the following properties. The first property is called as block coding. Block code means it is a code which maps each of the symbols of S into some finite sequence from X. Now, for example, if S is S1, S2, S3, S4, that means the information source is containing only 4 symbols and the alphabet set is only 0 and 1. All the 4 symbols have to be represented using 0 and 1. Now, there can be one example like this. There can be S1 as 0, S2 as 0, 0, S3 as 0, 1, S4 as 1, 1. This is one methodology. There can be another methodology, that is 0, 0, 0, 1, 1, 0, 1, 1. That is also possible. That is another methodology. I have been telling you that for a given problem, there can be multiple solutions. So it is not mandatory that we should have only one type of code. For every given symbol, there can be multiple types of codes which are again containing the source alphabet 0 and 1. So this is one example. S1 can be represented with 0, S2 can be represented with 0, 0, S3 can be represented 0, 1, S4 can be represented 1, 1. But now this is called as a block code. Why? Because our source alphabet contains only 0 and 1. Now source symbols may contain many. All the symbols will be represented only using these 2 source alphabets. Naturally it has to be so. Then it is called as block coding. In the 5th module, we are going to discuss one more type of coding called convolutional coding, where the source symbols can be represented by means of a polynomial. That we will discuss in the module 5. For the present context, just remember that block coding is nothing but the symbols being represented by the available source alphabets. Okay. That is the first property. Now, the second property is the code has to be non-singular. A block code is said to be non-singular if and only if all the code words are distinct and easily distinguishable from one another. Now, the code words mentioned above are not distinct. Why? S1, S2 and S2, S1. Let us see this. S1, S2 is 0, 0, 0. S2, S1 is also 0, 0, 0. Now, imagine this 0, 0, 0 is received at the receiver. Imagine that way. Let us see. I will write it here. Now, the receiver receives 0, 0, 0. Now, if the receiver receives 0, 0, 0, how will the receiver decode? Receiver may take the first 0 as S1 and next 2 zeros as S2. Now, receiver will have ambiguity. Receiver can also decode the first 2 codes as S2, first 2 zeros as S2 and the last 0 as S1. Which means what? Now, the receiver has ambiguity. This is the sequence. 000 is the sequence which is received at the receiver. Now this sequence is not non-singular, which means the sequence is not unique as such. Let me not use the word unique, because afterwards there is one more property called uniquely decodable. So, what is the meaning of non-singular? Non-singular means a sequence should be easily decodable at the receiver directly. There should not be ambiguity at the receiver. For that matter, this particular coding is having ambiguity. So, this code is not a non-singular code. It is basically a singular code. Okay. I hope you got it. Whenever the receiver gets a sequence, it has to be easily decoding the sequence without ambiguity or confusion. But there is a big confusion here. It can be S1, S2 also, it can be S2, S1 also. So, a block code is said to be non-singular if and only if all the code words are distinct and easily distinguishable from one another. For example, the code words mentioned above are not distinct. S1, S2 and S2, S1 will have the same sequence 0, 0, 0, and hence they are singular. Now let us have one more option of this code. S1 can be represented with 0, 0, S2 can be with 0, 1, S3 can be with 1, 0, S4 can be with 1, 1. Now in that case, this particular code is non-singular as all the code words are distinguishable from each other. 0, 0 is different from 0, 1, it is different from 1, 0, it is different from 1, 1. Whereas you see the previous example, this S1 is already contained in S2. This should not be there. This 0 is already contained in S2 also. It is already contained in S3 also. It is fine. S3 is fine because it is 2 bits. But S1 is contained in S2 also. That should not be the condition. So, the code should be non-singular that way. It should be distinct that way. All the code words must be distinct. That is the meaning. This is the second property. So, the first property is called block code. Second property is called non-singular code, where each code word has to be distinct and distinguishable. Now, the third property is called as uniquely decodable code. Let us see what does this mean. Now, a block code has to be non-singular. Now, the non-singular code has to be uniquely decodable, which means a non-singular code is said to be uniquely decodable if the original source sequence can be perfectly reconstructed from the received sequence. Whatever sequence is received, initially in the block code we discussed only about the representation of the symbol using the available character set called 0 and 1. In the non-singular code, we discussed about the distinguishable property of each code word. Okay. Now, when it comes to uniquely decodable code, we are thinking about a sequence of codes which are being transmitted from the transmitter, and a big sequence is being received at the receiver. Think about that G1, G2, G3, G4, like that it goes on. And we already know that larger the sequence length, lesser will be the number of bits used for representing the same information, and that way we are going to save the number of bits and there will be a saving in the resources. This we had discussed in the previous module. So, if there is a lengthy sequence now, that lengthy sequence has to be perfectly reconstructed at the receiver. For that purpose, the code has to be uniquely decodable. Now, for the codes mentioned above, if the received sequence is 00110001, then it can be decoded as S1, S4, S1, S2, because 00 is S1, 11 is S4, 00 is S1, and 01 is S2. But if at all, the very first example is utilized, if at all the codes mentioned in property 1 are utilized, then the problem there is you have the 0, 0. Then you have the 0, 0, 0. And we can say the sequence is not uniquely decodable now. Now, if we use the second set of coding, then the sequence is uniquely decodable. If at all we use the first set of coding, then the sequence will not be uniquely decodable. It will lead to ambiguity errors. So, if the codes mentioned in property 1 are utilized, then the received sequence can be S1, S1, S4, S1, S1, S3. Why? See, there is 0, 0. This can be S1, S1 also. Then again, this 0, 0 can be S1, S1 also. This can be S3. Or it can be S2 because 0, 0 itself is S2. Then S4, then S2, then S3. Or it can be S1, S1, S4, S2, S3. Or again, it can be S2, S4, S1, S1, S3. There can be 4 types of decoding at the receiver because the code is not non-singular and naturally the sequence is not uniquely decodable. When we mention the codes, we mention about non-singularity, but when we mention about the sequences, we mention about the uniquely decodable property. The second property is with reference to the code words, whereas the third property is with reference to the sequences. So, the codes mentioned in property 1 are not uniquely decodable. Such type of coding has to be discarded completely. So, this way we came to the third property. First one is block code, second one is non-singular code, third one is uniquely decodable code. Let me go to the fourth property. That fourth property is called instantaneous code. That is when I mentioned about the prefix property there in the Shannon-Fano algorithm. What is the meaning of instantaneous code? A uniquely decodable code is said to be instantaneous if the end of any code is recognizable without checking the subsequent code symbols received. For example, let us say a sequence is received at the receiver. As soon as a sequence is received, it is going to detect the codes one after the other. It is going to check whether it is 0 or 1, 0 or 1 that way. And the receiver must be able to exactly find out a particular code without waiting for the next bit. If such a code can be designed, then the receiver will not wait for the next bit. And it will immediately decode the bits that are received as per the sequence. I am going to show you the example later on. So now we are coming to the fourth property. This is a very important property. Important property in the sense non-singular code has to be block code and uniquely decodable code has to be non-singular code. Now the instantaneous code also has to be uniquely decodable code. These are all the upward requirements of the properties. A block code has to be non-singular. A non-singular code has to be uniquely decodable. The uniquely decodable code has to be instantaneous. Let me show you the example. Consider the following codes. We are giving you 2 examples now. S1 is 0, S2 is 10, S3 is 110, S4 is 1110. Second one, S1 is 0, S2 is 01, S3 is 011, S4 is 0111. Now let us say if the received sequence is 001100. If the received sequence is 001100. Now here you have 0. Let me annotate. Let us say we are using the first set. If you use the first set, here it is 0. Next here it is 0. So this can be S1. First one is S1. Next we have 0. Again it is one more S1. Next it is 1, 1. 1, 1 is not there in our code set. In the code set, 1, 1 is not there. So we have to go for, actually single 1 is also not there. So we have to go for 3 bits now. So it is 1, 1, 0. 1, 1, 0 is there. 1, 1, 0 is S3. And lastly 1, 0. That is again S1. So now it is S1, S1, S3, S1. This is going to be the decoding at the receiver if this first set is used. Okay. Let us say if the second set is used. Then what is the condition now? Let us say if the second set is used, I will write at the top here now. First is 0. So 0 is S1. Now next is also 0. Next is again, if at all I write it as S1. Now next is 1, 1. That 1, 1 is not there. That means I should not consider this first, after the first 0, I should not count this 0. I should wait for 0, 1 now. I should wait for the 0, 1. Now the 0, 1, this is ruled out now. 0, 1 is S2 now. Let us say at 0, 1 I complete. Again I get one more digit, that is 1. Should I consider 0, 1 now? No, this also I should not consider. I should go for 0, 1, 1 now. That means even this is not considered. 0, 1, 1 is S3. Okay, 0, 1, 1 is S3. Next, lastly, we have 0, 0. So this can be again one more S1. Again, there is one S1. Which means what? Using the first set of codes, we could instantaneously decode it without waiting for the next bit. As soon as we received that, we could instantaneously decode it. Because we know in prior, it is 1 bit, 2 bits, 3 bits, 4 bits. Here also it is 1 bit, 2 bit, 3 bit, 4 bits. But in the second set, we will have to wait for the next bit also to confirm whether that code word is existing in our code set or not. So this is where we have difficulties when designing the codes. Now, if the received sequence is 0, 0, 1, 1, 0, 0, as I told you, using the first code for decoding, the received sequence is S1, S1, S3, S1. As the end of the each code word is noted by a 0 there. You can see here, end of each code word is noted by a 0 in the first set. The first code is then instantaneous. We need not wait for the next bit to come. Whereas, using the second code for decoding, it is S1, S3, S1, S1. But here for decoding S3, we have to wait for the next bit. Even though I have written the correct answer, I wrote the correct answer after 2 iterations. That means after checking the next bit only, we have to decide that my previous decoding was wrong and I will have to cancel my previous decoding. I will have to wait for the next bit. So we have to wait for the next bit. This means that the second code is not instantaneous. Otherwise 0, 1 can be decoded as S2. Hence the second code is not instantaneous. Second code has to be discarded. Why? At the receiver, if the code is not instantaneous, receiver is losing its clock cycles in checking the next bit. So receiver is going to become slower now. Think about a digital system where both a transmitter and receiver are basically digital counterparts, and in the digital counterparts, they are all clocked. There will be having a system clock, and in each and every system clock's period, some operation is going to happen. When that operation is going to happen, if at all the system has to go for one more clock cycle for checking the next bit which is received, then whatever work was done in the previous clock cycle is discarded, or it's a waste of time. Now think about a system which is working in 4 GHz speed or 8 GHz speed, and think about the number of clock cycles wasted while decoding. Okay, so the code has to be instantaneous. To give you one live example, I am speaking now. My speech is getting into the laptop. In the laptop, there is this ADC where speech is getting converted into digital. It is going into the RAM of the system, and from the RAM, CPU is taking the streams of these zeros and ones, which are the digital conversion of my speech. Now, this digital converted thing, each sample has to be represented. Each speech sample has to be represented by a sequence now. That sequence goes into the modulator. In the modulator, there is a 2.4 GHz oscillator and there is a VCO. And using this 2.4 GHz radio carrier, the binary sequence is being transmitted through the antenna. Now that sequence goes all the way till your mobile phone or till your laptop, either wired channel or wireless channel. And in your receiver, you will have a demodulator after the antenna, where from the radio frequency of 2.4 GHz, it is demodulated and the binary sequence is obtained. When the binary sequence is obtained, again there is a DAC. Okay. Am I correct? No. DAC is at the other side. No. After the demodulation, because it's a digital communication, digital thing is available there. Now this digital information is going into the CPU, going into the RAM again. From the RAM, the CPU will take all these sequences. Now it has to decode. If it has to decode, now imagine it has to wait for one clock cycle, wait for the next bit, again it has to decode, and it is wasting the previous cycle. Again it has to wait for one clock cycle. If that happens at the receiver, it is going to be slower. If it is going to be slower, you will not be able to learn my speech instantaneously also. Right now between you and me there is a delay. That delay is only because of the communication delay in the channel. Okay, and there is a delay of latency which is there for digital signal processing. Even the processor will take a finite time for processing all these streams of bits. But if at all the processor is wasting each clock cycle for waiting for the next bit to decode, and then there will be heavy loss of timings there. That should not be compromised. Otherwise, system will become really very slow. A 2.4 gigahertz system may work with the half speed in that case. And later on, after it decodes, there is a DAC there. There is a digital to analog conversion. And after that, it goes to your earphone, and then you are going to listen to my speech. Now, between you and me, information theory and coding is working beautifully now. That means both my system and your system are having a code set of binary stream, and it is instantaneous code itself. But that code depends on a particular system, but it has to be defined as a standard throughout the world, where every laptop will use it, every mobile phone will use it, every desktop will use it, every digital communication system will use it for the purpose of voice communication. They have standardized all that. I'm not going to discuss all those topics. They are all quite advanced topics. If at all you study in future about this speech encoding and decoding, speech synthesis, people who are interested in studying more about digital signal processing, they will gradually study all those courses in their post-graduation. In the undergraduate level, we are unable to teach all those things as such. Even though we have electives, we are unable to teach as such, because no one will study those electives also. Why? If you are thorough with the signals and systems, then you will like DSP. If you are thorough with the DSP, then you will like speech processing and image processing. Now, for many of the students, full form of DSP is definite supplementary paper. That is the explanation which my earlier students have given. Even though DSP stands for digital signal processing, some students who do not clear that course, they make it as a definite supplementary paper. And whenever the same paper becomes critical, then they definitely call it as a degree stopping paper. This is where students coin their own abbreviations. Now, for those of you for whom signals and systems is interesting, naturally digital signals processing will be interesting. For those of you, if you make your career in future in signal processing domain itself, then if at all you pursue MTech or MS, then you will definitely study speech processing and image processing. And imagine we are dealing with information theory there, where each image sample, each voice sample has to be represented by means of a code, and the code has to be instantaneous. Only when the code is instantaneous, receiver will be as fast as the transmitter. Only when receiver and transmitter are compatible with the speed, then only there will be effective communication. Otherwise, there can be latency delay with video as well as audio. Sometimes that latency delay with video or audio is there, it is because of the system's constraints or the bandwidth limitations. But if the code is not instantaneous, then there will be a heavy delay in the regular digital communication itself, where the receiver is waiting for the next set of bits. That is why this is a very important property of a code. The code has to be instantaneous. This itself is called as that prefix property when I mentioned in the Shannon-Fano algorithm. The last property is called as optimal code. Optimal code means an instantaneous code is said to be optimal if it has minimum average length L. You are already familiar with the term capital L. Now for the given source, if it is having a minimum average length, then that is called the optimal code because it is optimum as such. So the 5 properties of the codes are code and block code. Code is a general term. Block code means we will have a character set and each symbol of the source is represented by a predefined character set. That is called block code. Now, block code has to be non-singular. That means non-singular is a subset of block code. Non-singular you already know. All the codes words have to be distinct. Now, uniquely decodable code is a subset of non-singular code. Means from a code word we move on to a sequence now. When we move on to a sequence now, the sequence has to be uniquely decodable. There should not be ambiguity. Now later on, uniquely decodable code has to be instantaneous, means there should be an instantaneous decoding at the receiver. It should not wait for the next set of bits to confirm whether it is matching with the code set or not. Finally, optimal code is a subset of instantaneous code, means it should have a minimum average length L. In that case, we will have a increased efficiency in the coding. So these are the 5 properties. Please understand them clearly and please remember them. Now there is a note. If any code word is a prefix of some other code word, then it can be immediately concluded that the code is not instantaneous. Such property is called as prefix property. Any code word should not be a prefix of some other code word. We had seen in our earlier examples that there was a single zero, there was a double zero. Now that single zero is a prefix of that double zero. That should not be there. If it is there, then only there is an ambiguity or confusion. So if any code word is a prefix of some other code word, then that can be immediately concluded that the code is not instantaneous. Such property is called prefix property. Means the code should not have such prefixes. Now this can be easily verified by observing the codes itself. We had observed those codes where 0 was also there, 00 was also there. And there was that prefix which was not expected. So it can be easily verified by observing the codes. Hence an instantaneous binary code can be constructed by taking care that no code is a prefix of any other code. While we encode any source symbol, we should take care that the code has to be instantaneous. But did we check it in the Shannon's algorithm? Did we check it in the Shannon-Fano algorithm? We did not check it. Why we did not check it? We did not bother much about all these 5 properties at that time. We only bothered about whether our encoding is efficient or not. We really did not check it. But now you can go back to all those examples, check in that notes, and you find out whether those codes are having these 4 properties, the first 4 properties. Block code is already there. But whether it is non-singular, uniquely decodable, instantaneous, these 3 properties you can verify. Non-singularity, you can verify. Uniquely decodable, you can verify. Instantaneous, you can verify. Now, why these 5 properties were not discussed at that time in the beginning? The reason is, again we go back to Shannon. At the time of Shannon, encoding a given symbol itself was a challenge which was accomplished by Shannon's algorithm. And at that time, nearly 5 to 6 decades before, or maybe 6 to 7 decades before, there was not this 2.0 gigahertz communication at that time. There it was maybe megahertz communication, where AM radio was there, FM radio was also there later on, but it was a communication using megahertz. Gigahertz was not there, terahertz was not there. So at that time they did not bother about the speed of communication. At that time there were no microprocessors and microcontrollers also. They came into picture later on after the VLSI industry flourished. Now we have microprocessors and microcontrollers, we have DSPs. But at that time, they did not bother about all these 5 properties. But now we have to bother. Now we have to bother because we are in the 21st century and we want speedy communication. Very high speedy communication we want. That is where even the chip design industry is moving from VLSI to ULSI to GSI to nano. And even in the information theory, we have to invent different types of coding methodologies so as to accomplish all our objectives. That is why these 5 properties were not discussed earlier. Now, based on these particular 5 properties, we will have a concept called craft inequality. I will start it now. I will not end it now. I will start it now. Now, I want to mention that for your test now, you will have syllabus till Shannon-Fano. Yesterday I told you that you will have syllabus only till Shannon's algorithm. But later on I have covered Shannon's Fano coding also. So for your test, you have to study till Shannon-Fano algorithm. Today I had discussed about the binary code and the ternary code. Till then you will have to study. Later on I discussed the properties of codes. Now I am discussing this craft inequality. These you can skip for the test as such. Now, what is craft inequality? If Q is the number of code words and if Li is the length of a particular code word, then K is equivalent to summation of I equals 1 to Q of 2 power minus Li. This is a necessary and sufficient condition for the existence of an instantaneous binary code, that is K should be less than or equal to 1. This is called Kraft-Macmillan inequality. Let me explain it once again. We have a set of code words and the number of code words is Q, and each code word will have a length that may be L1, L2, L3, L4 like that. Now we have to sum 2 power minus Li of all those code words. 2 power minus L1 plus 2 power minus L2 to 2 power minus L3 plus 2 power minus L4. In that manner, we have to sum all of them. When we sum all of them, if at all we get to K equals less than or equal to 1, then we can come to a conclusion that this is an instantaneous binary code. Earlier I mentioned whether the binary code is instantaneous or not can be checked by visible inspection. But visible inspection is possible only if the number of codes are 3 or 4 or 5 or 6. Imagine if the number of code words are, let us say, 20 or 30 or 50 or 100. How do you verify the instantaneous nature? That is where later on 2 scientists called Kraft and Macmillan, they found out a methodology in which we can check the instantaneous nature of a binary code by means of this expression, by means of this particular expression. K is equal to summation of I to the I equals 1 to Q 2 power minus Li, and K should be less than or equal to 1. If this is satisfied, then we can conclude that the given code word set is instantaneous. As I told you, in the lab, you can work with 1 transistor, 2 transistors, 3 transistors, maybe 5 transistors. You can connect them in the springboard or breadboard and you can check it. But how will you check if I give you 20 transistor circuit, 30 transistor circuit? Is it possible for you to physically connect 1 gigabytes of memory and check it? It is impossible for you. Even if it is possible, when you keep on testing it, you will become aged. It will take you many years to test the circuit physically. That is when we have EDA tools, electronic design automation tools such as Cadence and Synopsys and Mentor Graphics and Xilinx and all such things, where we use Verilog and VHDL, we use analog tools. Similarly, if the code words are much larger in number, it is not possible to check the instantaneous nature. We should have a different mathematical methodology. That is this methodology called Kraft inequality. More about this will be discussed in the next class after the internal test is over. I wish you all the best for your internal test. Study well and write well. I will see you